Hi everyone. So today we're going to talk about using series solutions to solve differential equations. And when we get started, I want to show you something about why we're even doing it this way. The big thing to keep in mind is that there's a lot of functions even in calculus that can't be represented in any sort of closed form, and yet they're things that we want to work with. So last section, we didn't really talk about why we want to use series to do things. I'd like to start by providing some motivation for why we use series at all. One of the more well-known problems from calculus that can't be solved with the techniques from calculus when you learn how to integrate is the integral of e to the x squared dx. So famously, this doesn't have a closed form. But the integral makes sense. E to the x squared is a super nice function. It's very smooth, and I can make it into a function that's very common as well just by writing down the integral of e to the minus x squared. So likewise, this doesn't have a closed form for the integral, but this function, e to the minus x squared, is one of the most commonly used functions in all of mathematics. It's the basis for the bell curve. If you plot it, it looks like this. And it's infinitely differentiable, and it's super smooth. So it's integrable, and its integral is nice. It just doesn't have an integral that you can write down in terms of elementary functions. And in fact, most functions in calculus don't have integrals that you can write down in terms of elementary functions. We've been working with a very small slice of those functions when we learn integration and differentiation. Now, we still want to be able to work with these functions. And so the best we can do is approximate them. And one way of looking at their approximations is to write down a series that represents this function. So in the case of e to the minus x squared, in the case of the integral of e to the minus x squared, we can use series to actually write down some form for this that I can use to either visualize what the function is or approximate it to however many degrees of precision I need. So if I want to know what the series for e to the minus x squared is, I could actually write down the series for e to the x, which is just the sum of x to the n over n factorial. And of course, you have that memorized, right? Because that's one of the series that you just have to have tattooed in your brain. E to the minus x squared is going to be the sum from n equals 0 to infinity of minus x squared to the n over n factorial, which I could then write as the sum from n equals 0 to infinity of minus 1 to the n over n factorial times x to the 2n. And so this is about the best we can do for the series of e to the minus x squared. That's great. This series converges everywhere, so it has an infinite interval of convergence. And once I have a series like this for this function, remember that I can treat it like it's a giant polynomial. So if I want to integrate a polynomial, what I do is I integrate it term by term. And I can do exactly the same thing here. Remember, the goal here is to give you motivation for what we can do with series that we can't do with elementary functions. So thinking about the function as an infinite series, I can replace e to the minus x squared with the power series that represents it. Remember, that converges everywhere, so it's a completely valid expression to write down. Since I can think about a power series that converges as a polynomial, I can just take the integral and I can put it inside on every term. And that's going to let me write something like the integral of 1 dx minus the integral of x squared dx plus 1 over 2 factorial times the integral of x to the 4th dx, and so on, which is actually easier to write in sigma notation as the sum from n equals 0 to infinity of minus 1 to the n over n factorial times the integral of x to the n dx. So the justification for taking the integral and putting it inside like this is we're thinking about this as a giant polynomial. And then that lets me write down an expression for the integral of e to the minus x squared, minus 1 to the n over n factorial. I've got to increase the power of the x and then divide by the new power. And that means that I could rewrite this as the sum from n equals 0 to infinity of minus 1 to the n over n plus 1 factorial times x to the n plus 1. And so this expression right here, that's about the best we can do. This is the integral of e to the minus x squared. And if I'm trying to figure out the value of the integral of e to the minus x squared somewhere, I can take an x and I can plug it in here, and I can just add and subtract terms until it gets stable numerically. So the idea is most functions are made of power series that do not have closed forms. And so most differential equations are not going to have solutions that are e to the x or cosine of x or sine of x. They're going to have solutions that look like power series. So we're acquiring new restrictions when we assume that a function has a power series. but we're also gaining access to a lot of problems that we can't do with the techniques that we learn in the elementary version of the differential equations. So now to flip to our topic matter, if I'm looking at differential equations, in earlier classes we learned a whole lot of techniques for working with first order equations. And we learned a really specific technique for a certain kind of second order equations. So the most common equation that we solved were things where we had ay prime prime plus by prime plus cy is equal to 0. So homogeneous, second order, linear differential equation with constant coefficients. And what you learned is that you take the coefficients and you write down something called the characteristic equation. So this is called the characteristic equation. And then you factor that. And that will factor as something like m minus r1 times m minus r2 is equal to 0, where r1 and r2 could possibly be complex numbers. And depending on if the roots are distinct or not distinct, you learned that the solution set to this differential equation looks like y1 is equal to e to the r1x, and y2 is equal to e to the r2x. And then by the principle of superposition, you learned that the general solution for this is c1 e to the r1x plus c2 e to the r2x. I'm not trying to go through examples here. I'm just trying to remind you of the technique that you learned. This is one of the most important techniques in differential equations. But it comes with a major restriction, which is that the only equations we can solve are equations that have constant coefficients. What happens if we introduce a coefficient that is not a constant? So I'm going to make a very simple modification to a second order linear differential equation, and it will completely break all of the methods that we've learned so far. So this is called Aries equation. An Aries equation originates in the study of optics. All I've done here is I've introduced an x in one place in the equation, a single non-constant coefficient. And as soon as I do that, all the techniques that we've learned fall apart. This is an equation that is not in one of the special forms that we know. It's not a Cauchy-Euler equation. There's no pre-programmed set of solutions we can come up with for this. It came out of physical applications. It's not really possible to reduce this to a constant coefficient equation. Just this simple equation where I put a single x right here has completely changed the nature of this differential equation. And we need an entirely new set of techniques in order to solve it. So the point is, elementary techniques do not work. And the reason that they don't work is that the solution to this is not a function that has an elementary form. The solution to this equation is made out of power series, and those power series don't have closed forms. There's no way to write solutions for this equation down that are not power series. That's the big argument for using power series, is that we get access to a family of equations that arises in physical applications that we don't have any other technique for solving. So the first thing that we want to look at when we're thinking about differential equations with series solutions is we need to make sure that the differential equation supports a series solution. Remember that if we assume that a function has a power series, we're assuming that the function is analytic. So to assume that f of x has a power series is to assume that f is analytic. That's almost a tautology because we defined analytic to mean f has a power series on some interval of convergence with a positive radius. How do we know that the equation that we write down supports that? Well, if the answer is going to have a power series that converges on some interval of convergence, then the equation needs to be built out of things that have the same properties. So the general form for a second order linear differential equation with non-constant coefficients is y prime prime plus p of x y prime plus q of x y is equal to 0. And p of x and q of x you can think of as coefficients, but they're not constant coefficients. They're functions that are modifying things. If we want it to be the case that the solution to this equation has a power series, then all of the pieces that make it up have to have power series as well. If these pieces, the p of x and q of x, aren't analytic, that is, they don't have some power series representation, they're not super well behaved in some interval, then it can't possibly be the case that the solution does. We're not going to get access to every single possible equation that we can write down this way, but we do get access to equations that are analytic. And in some cases, we get access to equations where the functions are well behaved on pieces. They might have asymptotes, but as long as we stay away from the asymptotes, we can still assume that the function that solves this has a power series. So the definition here is that we say that a point x is an ordinary point for the equation if p of x and q of x are analytic at x. So if I have a point x, and as long as p of x and q of x have power series representations, which really for most cases for us is going to involve staying away from asymptotes, then I can assume that the solution has a power series representation. And the first thing we have to do is identify when we look at an equation, one, it's in standard form, and two, that I've stayed away from any asymptotes that p of x and q of x happen to have. So what we're going to be doing is we're going to be assuming that the solution to a differential equation like that has a power series representation, and then we're going to try to find the coefficients of the power series. So the goal of this method is that we want to assume that y has the form of a power series, and then we want to find the coefficients. And there's a method for finding the coefficients that we're going to walk through that's sort of arduous. It's not difficult, it just takes a lot of grinding. One thing that you may have noticed is that when I write power series down, typically what I'm doing is I'm writing down power series in terms of x and not x minus x naught. And the reason is that if I have a power series that's not centered at 0, I can always shift it to be at 0 by doing the substitution x minus x naught gets replaced with u. And then you can just shift all the variables in your equation. And so really, it's enough just to consider power series that are centered at 0. It makes the formulas easier to write down. The way that we're going to find the coefficients is we have to come up with what's called a recursive equation. But in order to get it, I need to have expressions for the derivatives of a power series. Recall from last time that I wrote down some expressions for the derivatives of power series. I'm going to write them again because we're going to be using them this time. We're going to take the expressions for the derivatives of power series and we're going to plug them into the equations to try to get some sort of description of how the coefficients are being generated. So we need to remember that if y is equal to the sum from n equals 0 to infinity of an x to the n, that typically what we write down is that y prime is equal to the sum from n equals 1 to infinity of n an x to the n minus 1, and that the second derivative we write down as the sum from n equals 0 to infinity of n times n minus 1 an x to the n minus 2. So those are just symbolic derivatives. These are the expressions that we're going to plug into a differential equation to work with it. What I'm going to show you first is an example where we go through an equation, we verify that it is analytic, and then once we know that it's analytic, we're going to assume that the solution is of power series, and we're going to walk through the process of describing what the coefficients have to look like. So let's start with an equation that we already know how to solve with a different technique. So consider the equation y prime prime minus y is equal to 0. This equation is very easy to solve. And the reason that it's easy to solve is because we can write down the characteristic equation, m squared minus 1 is 0, which factors as m is equal to plus or minus 1. And so that means that we already know that the solutions to this are y is equal to c1 e to the x plus c2 e to the minus x. This is an equation we can access with techniques we already have because it has constant coefficients. But the power series method still works here. And it will give a good way of walking through the process of how we use a series solution. How are we going to apply series methods to this? Well, let's start by checking that it meets the assumptions of analyticity that we need. If we think about the equation y prime prime minus y is equal to 0, really that's the equation y prime prime plus 0y prime minus 1y is equal to 0. And so p of x is equal to 0. That has a power series. It's conversion everywhere. There it is, 0. And q of x is equal to minus 1, also an analytic function. Okay, every polynomial is analytic. And so that means every x is an ordinary point because p and q are analytic everywhere. Let's assume that we have a series solution to this equation. So we'll assume that y is equal to the sum from n equals 0 to infinity of an x to the n, that y prime is equal to the sum from n equals 1 to infinity of n x to the n minus 1, and that the second derivative is the sum from n equals 2 to infinity of n times n minus 1 an x to the n minus 2. So let's take those and we're going to plug them in to the differential equation. So y prime prime is the sum from n equals 2 to infinity, n times n minus 1, an x to the n minus 2. And then I have to subtract off y, which is the sum from n equals 0 to infinity of an x to the n is equal to 0. And what I'd like to do now is I want to try to combine these equations in such a way that I can get these expressions for an together. So I need to somehow squish these two power series together using algebra. So there's two rules that I need to follow in order to take two series and put them together. The first is the powers of the x terms need to match. That is, I need to be combining like terms. And right now we don't have that because we have an n right here and we have an n minus 2 right here. The second thing I need to do is I need to make sure that the indices match. That is, the starting point of the series has to match on both sums. So I've got an n equals 2 right here and an n equals 0 right here. And so I have to have some formula that starts at the same place so that, again, I'm comparing like terms. So all of this is about getting like terms together. I'm going to do it in the order that I've described them. I'm going to make the powers match first. After I do that, if the starting index doesn't match, then what I'll do is I'll just drop terms off some of the sums until I've got something that does match. So let me show you exactly what I mean by that. So here's the equation that we're starting with. And what we're going to do is we are going to first make a substitution that changes this x minus, or this n minus 2 into an n. So what we can do is we can shift all of the n minus 2's by making, for the moment, we can just change to a different variable. So let's let t be equal to n minus 2. Because then if I replace n minus 2 with t, then that will mean that the series is x to the t. There are going to be n's that occur in the sum. There's an n right here and there's an n right here. When I replace the n minus 2 with t, I'm going to have to replace n with something. And just like in u substitution, I can solve this expression to get this one. Everywhere I see an n, I can replace it with a t plus 2. And then over here, I'm just going to let n equal t just so that the variables match. I don't need to make any changes there. There's no shifts, but I'd at least like to keep the variable the same. So what happens after you do that? Well, the original sum started with n is equal to 2, but t values are n minus 2. So this series starts with t is equal to 0. N gets replaced with t plus 2. N minus 1 gets replaced by t plus 1. There's an n as the subscript of the a. That gets replaced with t plus 2. And then we have x to the t. The second sum stays the same, except we've changed the t variable for an n variable. And now we have to check. Have we met the two conditions? Do the powers match? And the answer is yes. There's an x to the t on the left sum and an x to the t in the right sum. 2. Does the starting index match? And the answer is yes. This series starts at 0. This series starts at 0. So now what we can do is sort of like an infinite factoring. If we think about this as a polynomial, I could take each of these terms and I could pull x of t out of each of them. What that means is, using the algebra of power series, since the powers match and the starting indices match, I can write this as one sum. The sum from t equals 0 to infinity of t plus 2, t plus 1, at plus 2, minus at. Then there's the x to the t that I've pulled out of all of it. And so now I've got a one-sum version of this equation, where this is a single power series now, just with this complicated expression for its coefficients. So that is going to be the thing that we work with when we're trying to describe what the coefficients of the power series are. Because again, if I know the coefficients of a power series, I know the power series. Now we're going to use a rule that holds for polynomials and convergent power series, which is that if a polynomial is equal to 0, or a convergent power series is equal to 0, all of the coefficients have to be equal to 0. There's no way that we're going to be able to get a polynomial or a power series to be equal to 0 unless every single term is equal to 0. And so this is the big trick. Once we have a single power series, we can throw all of the sum and the terms away and just look at the coefficients. So the fact that we have a power series that's equal to 0 means that the coefficients are equal to 0. This is equal to 0 for every value of t. T plus 2 times t plus 1 times at plus 2 minus at is equal to 0 for t equals 0, 1, 2, etc. There's actually a more useful form of this where we can solve for at plus 2 in terms of at by just doing some algebra. And what we'll get is that at plus 2 is equal to 1 over t plus 2 times t plus 1 times at, for t is equal to 0, 1, 2, and so on. So what I can do with this expression is I could plug each one of these t values in, and it's going to give me a different equation relating the coefficients of the power series. So let's just start plugging in some values and see what we get. And this process is called a recurrence relation or a recursion, because previous information is going to tell us about future information, which will become clear when I start writing the equations down. So we have the equation at plus 2 is equal to 1 over t plus 2, t plus 1, at. So let's put in some values and see what happens. If I put in t equals 0, I get the equation out a2 is equal to 1 over 2 times 1 times a naught. So if I put in t equals 0, I get a relationship between 2 and 0. If I put in t equals 2, and there's a reason I've skipped 1, we'll come back to 1. If I put in t equals 2, I'm going to get the equation a4 is equal to 1 over 4 times 3 times a2. But I know a2. I know that a2 is equal to this expression. And so that means all of this becomes 1 over 4 times 3 times 2 times 1, a naught. So I can get an expression for a4 in terms of a naught by doing this substitution. Conveniently, this is also equal to 1 over 4 factorial a naught. And this is 1 over 2 factorial a naught. If I put in t equals 4, I get the relation a6 is equal to 1 over 6 times 5 times a4, but I know that a4 is equal to 1 over 4 factorial. 4 factorial times 5 times 6 is 6 factorial. Okay, so it looks like that if t is even, then we get this relation that says when the index down here is 2, you notice there's a 2 factorial right here, and this is 2 less than that. And when there's a 4 here, you get a 4 factorial in the bottom, and you still get this a naught out here. And when there's a 6 here, you get a 6 factorial, and there's an a naught right here. And to me, what that suggests is that the general form, when t is even, of the coefficients a, k, is 1 over k factorial a naught, right? And so what that really describes, because remember that the a n's go with an x to the n term, is that we get a series that looks like a naught plus a2x squared plus a to the 4th x to the 4th, and so on, which, because I know expressions for a2, a4, and a6, I could write as a naught plus, well, what was a2? a2 is 1 over 2 factorial a naught x squared plus 1 over 4 factorial a naught x to the 4th. And then I could pull the a naughts out of everything, and I would get a naught times 1 plus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th, and so on. And so this object right here, that is one of the solutions to the original differential equation. It doesn't look like the power series for e to the x or e to the minus x, but it will become clear why in a second. The idea is that I have constructed one of the solutions to the differential equation in terms entirely of the initial data a naught. And the other solution will be in terms of the initial data a1. So a naught is some unknown. I don't know that. I have to tell you some physical condition in order to make that have a number attached to it. But that is the arbitrary constant that determines how much of that solution is present in the general solution. And so this is it. This is y1. We found one of the solutions in terms of one of the initial conditions of the series. For the other one, we could write down the same sorts of equations. When we put in t equals 1, we're going to get the expression a3 is equal to 1 over 3 times 2a1, which is 1 over 3 factorial a1. If I put t equals 3 into the recurrence, we get a5 is equal to 1 over 5 times 4 times a3, but I know a3. This can be written as 1 over 5 factorial a1. If I put in t equals 5, likewise, I get a7 is equal to 1 over 7 times 6 a5, but I know a5, and 7 times 6 times 5 factorial is 7 factorial, so I get 1 over 7 factorial a1. And what that means to me is that when t is odd, I get a relationship that looks like ak is equal to, well, this matches this, And all of these are in terms of a1. So ak is equal to 1 over k factorial a1. And that means we can write our power series as, remember, these are odd terms, and a3 goes with x to the third, and a5 goes with x to the fifth. That means that we could write down a1 plus a3x to the third, a1x plus a3x to the third, plus a5x to the fifth, and so on. Could be written as a1x plus 1 over 3 factorial a1x to the third, plus 1 over 5 factorial a1x to the fifth, replacing all the coefficients with their expressions in terms of a1. Factor out a1, and you get a1 times x plus x to the third over 3 factorial, plus x to the fifth over 5 factorial, and so on. And there's our second solution in terms of a1. Notice that also doesn't look like e to the x or e to the minus x. So this is y2. What the theorem says now is I've got expressions for y1 in terms of a0 and y2 in terms of a1, and by the principle of superposition, the solution to the general equation is the sum of those two things. So what we've shown is that for the equation y prime prime minus y is equal to 0, the general solution is equal to a0 times 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial, and so on, plus a1 times x plus x to the third over 3 factorial plus x to the fifth over 5 factorial, and so on. And now you might wonder how we get from here to the solutions that we wrote down using the characteristic equation. After all, these are supposed to be unique. And the answer is yes, the general solution is the same, but it doesn't have to be expressed in the same way. In the same way that a vector could be expressed in lots of different combinations of two vectors, the general solution to a differential equation can be expressed in many different ways as well. So you'll notice in our characteristic equation version, we had the solution yg is equal to c1 e to the x plus c2 e to the minus x for some unknown constant c1 and c2. So in the bottom equation, because these are arbitrary, and I'm going to show you guys that both solutions can be recovered from each other, if you let c1 be equal to 1 and c2 be equal to 0, this just turns into e to the x, which means e to the x is one of the solutions to the differential equation. Well, what happens if I let a0 and a1 be 1? If I let a0 be equal to 1 and a1 also be equal to 1, then those two series add together. And what they add into is 1 plus x squared over 2 factorial plus x to the third over 3 factorial, which is just e to the x. So the coefficients are different, but the solutions are the same. So what we have is a set of two linearly independent solutions that is equivalent to the solutions that we had here. So this set of solutions is in terms of the exponentials. This is in terms of these power series, but the way that these combine gives you the same set of possible answers as the way that these combine. In relationship with vectors that you've seen before, what we've done here is we've expressed the same solution set, but with two different coordinate systems. And we're going to move on to a more complicated example in the next video, but you should keep in mind the process that we went through to get our solution. So we checked that in the equation y prime prime plus p of x y prime plus q of x y is equal to 0, that p and q were analytic, which is to say that we had x is an ordinary point, and we did that for x is equal to 0. 2, we assumed that we had a series solution y is equal to the sum from n equals 0 to infinity of a n x to the n. We used algebra and a recurrence relation to write our general solution as a0 times some function y1 and a1 times some function y2. A lot of algebra there and looking for patterns. And hopefully when we look at another example, we'll see that the patterns don't necessarily look as nice as they did in this case. But this is the core technique for working with series solutions, is to write down a recurrence relation, to uncover what the relation is between the coefficients, and to write the solution in terms of a0 and a1, which you can always do if you use this method at an ordinary point. All right, see you for the example.